Good evening, everyone. Welcome to the live session. So, today we'll be discussing practice problems from week 5's content. I'm Paulumi, I'm one of the TAs for the NPTEL Natural Language Processing course. So, like every other session, we'll wait for 5 minutes for everybody to join in and we'll start at 7:05. Okay, good evening, everyone. So, let's get started with the live session. So, this is the first problem for today. So, we have been given a few statements. We need to say which of the following are true. So, please try solving the problem and we'll wait for a couple of minutes and then we'll discuss the solution. So whoever is able to solve the problem, please post your answers in the chat. So we can start from there then. So is there anywhere people are stuck? So nobody has still posted the answer. Um, so that is why I'm asking: is anybody stuck at any point? So it would be great if you can also just attempt it once for the sake of it. Then anyways you would be discussing. So we have got one answer from Premalata. How about others? Okay. Okay, let's discuss the problem. The two of you have answered. So Premalata and SS Barpe. So both of you think it's options A and B. So Premalata, would you like to say why you think option A is like the correct answer? Yeah, good evening, ma'am. Yeah, good evening. Just it's a guess, ma'am. Okay, okay. So how about both A and B? You think so? Any idea about why B is the correct answer? Any idea? So anything that you would like to add? No, ma'am. Okay, okay. How about SS Barbe? Would you like to comment why you think A and B are the correct answers? So it doesn't matter whether it's wrong or right. We are just trying to hear what everybody is doing. So just an attempt, if you would like to.
I can say about option C.
Okay, yes, please go ahead.
Actually, in compiler design, my teacher had taught us that that CNF requires 2n minus 1 number of steps to generate to work in string W.
Okay, yeah, that's correct. Okay, so that is why C is an invalid option. Right,
Yes, ma'am.
right. Uh, Vandana is saying that A is correct because CNF is generated from CFG and they are both okay. Okay.
Madam,
Yes.
you can create more than one CNF form for a given graph. That's why true. and I think A is also true.
Okay, okay. Uh, all right. So this was Vandana, or I did not catch your name.
Perfect.
Okay, okay, okay. Okay, fine. I think we can discuss the official solution now. So it's indeed A and B. So why is that the case? So first, let's discuss what is CNF, what is the Chomsky normal form. So there are two rules or restrictions that are placed. So either exactly two non-terminals should be there on the right hand side, or there should be one exactly one terminal symbol on the right hand side. So these are what constitutes the Chomsky normal form. Now, why is the first option correct? That given a CFG context-free grammar and its corresponding CNF, that is Chomsky normal form, they produce the same language because Chomsky normal form is just the normalized form of the context-free grammar. They basically contain the same grammar rules, and that is why they'll produce the same language. For the second option, for a given grammar, there can be more than one Chomsky normal form. So let's look at an example. So this is from the lectures only. So this is one taken from the slides. So here we can observe. So when we have such cases that S is auxiliary, noun phrase, and verb phrase. Here what we can do is on one hand we can club. So here what we have done is here we have clubbed auxiliary and noun phrase. And that has given us one production rule, and another one is we just simply plug in x1. So x would be from S would be from x1 to VP. On another hand, one thing that we can do is instead of clubbing the first two, we can club NP and VP as well. So instead of X1 being auxiliary and noun phrase, in that case we would have NP and verb phrase. And over here, that would give us a different production rule. That would give us auxiliary and X1. So this is one example where we can see that we are getting multiple Chomsky normal forms for a given context-free grammar. Okay, so that is why the option B is also correct. Now let's discuss option C. So one of you already told that there would be Cn minus 1 rules. So why is that the case? Let's just elaborate a little bit on that. So let the length of the string that we are handling, let the length be n. So in context-free grammar, one thing that is very important, just to reiterate again, that each non-terminal can give exactly two non-terminals. Okay. So, or there could be other cases, we could have one terminal symbol. Okay, these are the only two possibilities. Now, say we start with S. So, S is a non-terminal symbol. So, from that, additionally, we can use n minus 1 rules, which would be of this form, non-terminal to non-terminal to non-terminal. Okay, and now from this, what we would obtain total n non-terminal symbols. And from each of these non-terminal symbols, I can have, from each of the individual non-terminal symbol, I could apply a rule of the form non-terminal to terminal. And so ultimately, I would get a string of length n. And how many rules that I applied? So it was n minus 1 plus n. So n minus 1 initially were of these form, and finally the n rules were of this form. So non-terminal to terminal, so total 2n minus 1 rules. Whereas in the option it was given as 2n plus 1. So this makes option C correct. Oh, sorry, incorrect. Okay. So that is why we have A and B to be the answer. Um, so this was the solution. Does anybody have any doubt? Okay. Okay, so we'll move over to the next problem. In case anybody has a doubt, we can come back to this. Okay. So this is the second problem. So we are given a context-free grammar. Now we have to answer how many non-terminals should be added to convert the context-free grammar to its corresponding Chomsky normal form. So this can take a few minutes. So please try all the steps and post your answer. Then we'll take up, like, we'll go step by step and finally solve it as well.
And we have a respective grammar to be referenced.
For this problem, no. These are only, so two production rules are given. This is on basis of this itself you have to solve. Yeah, so Roshan Lal is asking to, can you explain the concept of CFG? Why is it called context free? So it is called context free because whenever we have a non-terminal which we are elaborating, irrespective of whatever context the non-terminal appears in, we would be able to derive the same production rules. So this was even discussed in the slides. I'll maybe take up an example that would be better. Just a second. Okay, so I hope this, so I'm now sharing the slides. I hope this is visible. So here we can see, so we are exactly addressing the question that you asked. What does context stand for in context-free grammar? So here context stands for, so whenever I have the non-terminal on the left-hand side of a rule, so irrespective of whatever context, so free of the context of where it appears in, I could apply it. So for example, here we have A to BC. So I can rewrite or I can expand A to be equivalent to B and C regardless of whatever context it appears in. So there could be an X before it, X before A, or there could be a C after A. That doesn't matter. Wherever I have A, I can simply expand it and replace it by a BC. So that is what it means. So it is not dependent on whatever is present before it or after it. Is it clear, or should I explain it again?
And which I can get some inputs from this question number 2 actually.
Hmm.
That S is a sentence again within recursive sentences,
Yes, yes.
and D is a determiner.
So D is a random non-terminal. So nothing specific in this case.
Okay, and the pipe indicates
So it means that S
it's
could be,
S as a D or S as a S D, is it?
yes, two options in which S could be expanded as.
And the D determines again a recursive D or C is a
So D could either be expanded as a DC or it could be null.
none, is it?
Yeah, this is a null string, yes.
XMM,
Yes.
there will be the CFG into CNF at most and at least 5 known terminals here.
Okay.
As determine A as B, we will convert small a and b in uppercase and then we will convert into A determine BC form.
Okay, so you think your answer is 5, right?
Yeah, as determine D,
Okay.
it means we convert in terminal B determines small d here.
Okay, so I think just we'll wait
But
for a
D
couple of
determine
minutes.
epsilon,
I think
D
people are
determine
still
is epsilon
solving.
also. Yeah,
Just
A
a
determine
second.
is epsilon, then we have to eliminate epsilon also there.
So I was saying that people are still solving. So we'll wait for a couple of minutes and then I'll ask you to tell your approach. Yeah. The example Roshan last, we have given two production rules. One is AB to CDE and another one is DFE to FTY. So these are completely different production rules. So say on the left hand side you have EA on one hand, on another hand you have A and F. Okay, so these are two different things. So two different contexts, right? On one context you have E appearing before A, and another one you have F appearing after A. So they are different contexts. Now, what context-free grammar does, so if I have a production rule saying that A should be elaborated as A should be expanded as B to C, so irrespective of whether E is appearing before A or F is appearing after A, it doesn't matter. So there could be some D appearing after A as well. So that doesn't matter what is coming before or after A. Wherever you see a, irrespective of its context, irrespective of what are the surrounding non-terminals and terminals that are present, irrespective of that, you can simply, wherever there is an A, you can extend it to a BC. Or again, so if the rule was A to BC, so I'm typing in the chat. So the rule was this. So wherever, so in this case you had EA. So in EA can be expanded as so E BC. Similarly, AF would be expanded as BCF. So it doesn't matter what is coming before and after. Similarly, if at any place if you see a BC, BC can again be inferred back as A. So that is what it means. Whereas the examples that you were giving us, so we have to focus on the same non-terminal and terminals. Like so the production rule has to be constant. So consider one specific production rule, and then you consider what are the variables appearing on the left hand side and right hand side, and you place it in different contexts. Now, whatever be the context, it would be expanded or inferred the same way. So that is what it means. Is it clear now?
Yes, ma'am.
Okay. So Vandhana Rajput is saying, ma'am, can you solve in written form? So the same thing that I was explaining, what does context mean in context-free grammar? That is where you have the doubt in. So Vandhana, could you just explain what is the question that I need to clarify?
Actually, ma'am, I want to know the step-by-step process. How did you do?
How to do the question two? Or
How did you do solve this?
the question two you're saying, right? Or the thing that I was explaining.
Yeah, I want to know in the written form. Actually, there is doubt. Doubt is this: whenever we are, the first step is like one step is to remove the null production. So for removing the null production, we will replace the D with the uh, F silent. So it will remain the same. So just I want to know the clarification.
Okay, okay. Okay, yeah. That will take up. That will take up. In this problem itself, we'll take up all those steps. So we'll discuss that. Um, So I think someone was explaining the problem when I had, so when I was saying, when I asked you to talk, you can explain now. You had got the answer to be five, right? You can explain what your, uh, how did you come to it, and then we'll jump to the official solution directly. So sorry, I did not catch your name though. So if you're still there in the live session, you can please unmute yourself and you can explain.
I'm Lokesh ma'am. I just try it out and I found it is that the non-terminals is just to be defined to come up with the
Okay. So, so where did this three non-terminals? So what were the steps that you followed? Just very briefly.
Yeah, I split S as and non-terminal, again the S with a CS, and again non-terminal as one rule, and again S deriving to D as one more separate rule.
Okay.
So in which we have two non-terminals which is not defined here, A and B.
Okay.
And coming to D, we have a definition for D, and for D we have D and DC. Here we have another non-terminal C which is not defined.
Okay.
With
Okay.
knowing the values for all these three, we can come up with this
Ah,
SEM.
okay. 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 Mm,
I basically depend on this number of unknown variables. I mean, non-terminals which are not defined in the rule.
okay. I think you splitted the rules. I think maybe is there a chance of some rule getting depleted as a result of that? I'm just asking.
They mean can be excluded.
Hmm.
Mm, ultimately, a non-terminal has to end up with a nominal or another non-terminal, right?
Hmm. Yes.
And so in which A and B are never known what is a non-terminal, whether it is either into nominal or it's again a non-terminal.
Okay. Okay. All right. Okay, so I think now we can just discuss the official solution once. So the answer is D actually. So it's 5. So we'll go step by step and see how it is happening. So initially we are given just these two production rules. So one is from S we can derive A as B or D. Another one is from D we can derive DC or epsilon. Now there are certain there are certain rules or some specific procedures that we need to follow to go from the context-free grammar to its corresponding Chomsky normal form. The first is we need to check that if the start symbol is occurring on the right hand side of any production rule. So we see that is so in this specific production rule, the first one, we see over here there's an S that is appearing on the right hand side. So we need to take this into account and we need to do some modifications. So what it is? So just to reiterate, since the start symbol S occurs on the right hand side of the production rule, we what do? We create a new start symbol S dash and we add a new production rule S dash to S. Okay, so here we see. So what has changed? So we added this new start symbol and we added this production rule S dash to S. After that, everything is as it is. We are just rewriting the production rules that were already there. Okay. Next, what we do? Next, we need to remove the null productions. So what are the null productions in this case? So there are two null productions. One is d to epsilon. Another one we see is d is also appearing on the right hand side of s. So from s we can derive d. Again d leads to epsilon. So s can also derive epsilon. So there are two null productions over here, d to epsilon and s to epsilon. So we need to remove them one by one. So let's start with removing d to epsilon. So what do? We check each of the production rules and we see where is d appearing on the right hand side. So in this one there's no d, so we retain it. In the next one we see there is a d occurring over here, so we replace it by epsilon. So here we see the modified rule. The first part is as it is. So S deriving A is B or D. Alongside that, we add an epsilon. So that takes into account that this the fact that D could also extend to epsilon. So that is why we are adding this. So this now becomes one more possibility in which S could be derived. Okay. Next is this rule. So here we again see that there is a D on the right hand side. Now if we replace d by epsilon, we only get c. So again, retaining what was there already and just adding this c that we got from here. Okay. So is this step clear for everyone? How we are handling the how we are removing the null production?
Yes, can explain.
Yes, sure. So let's first understand what is a null production. So null production is somewhere. So null production is for this case. So see, here we had a rule that d can be derived as epsilon. So such examples where I have a non-terminal on one side which could be expanded as a null string, so those cases are considered as null productions and we need to remove it. So we first find what are the different null productions that are there in the latest production rule. So this was my latest production rule. So one I can find d, this in this production rule, d is deriving epsilon. So this is one non-production. Another one is here we see s is deriving d and d is again deriving epsilon. So s can derive epsilon as a result of this. So these are the two null productions. So first we handle this one. So first we are removing the null production d to epsilon. So for that we see in each of the production rules where is d present on the right hand side. So in the first one there is no d on the right hand side. Here we find there is a d. So what we do is we replace d by epsilon over here. So what do we obtain? So what would be the modified rule? So the modified rule would be first we write the rule as it is, how it was. So it was initially S to A S B or D. So we have S to A S B or D, and what we get as a result of removing the null production, this D to epsilon. That is epsilon we got, right? So we add that. Now we move on to the third rule. So here again D.
Nullifiable, nothing but it ends when it's in a nominal or weak mode.
No, null string is equivalent to null or nothing. It's a null string. So when nominal or those are valid terminals. So valid non-terminals or terminals. When there's nothing, or you can think of it as an empty string. So that is what is epsilon. When it's emitting nothing. Hmm.
So in the grammar, they do mention nullifiability.
Yeah, and the grammar is there. This was the rule, original rule, right? D to epsilon. You see this epsilon term over here? So it means that D could indeed be expanded as epsilon.
Actually, in the weak question, so you know that not was actually nullifiable point. Only I found valid nominal or if it is a recursive method.
Okay.
Then anything is with differentiation.
Um, so, um, so could you give an example of what you're
CMS, I
saying?
just found to the sessions of the time.
Mm-hmm.
Then I noticed a grammar with nullifiable.
Okay, I think in the slides the example that Sir had discussed. So Sir had, I think, discussed for one of the examples. So this one itself, right? This one Sir had discussed how to go from the Chomsky, go from the context-free grammar to a Chomsky normal form. Here nothing was there, right? Here you can see there's no null variable. Can you see?
Yes.
right? So I think this was not handled. So this was actually the null variable was not handled in the classes, but it was there in one of the problems. So I took it up.
Okay. So as part of this HTML grammar, we can have this modifiable rule also.
Yes, yes. So Chandrakala has raised a hand. Yes, do you have a doubt? Okay. Vandana has raised her hand. Yes, yes, Vandana.
Ma'am, in the solution, where we solve the question, the stand to B
Hmm.
as as this implies to epsilon.
Hmm.
So in this step, we cannot change the um, as dash implies S. So here we cannot change the S with epsilon
The
in the
first one?
first. Yes.
No, first one we don't change. So this is this is a rule that we added, right, as a consequence of the first. So so there was this what do you call? So there was this situation that we had S on the right hand side, right? So to account for that, we had added this. So in this we need not do the multiplication.
And is that the notation we have to follow S on the other start symbol?
S is usually followed as the start symbol. So
So for our understanding, we can label it something else also, right? Instead of S dash, we can have it as start.
yeah, you can. Yes.
So ma'am, in this
Hmm.
question, if I tell in conversion of CRG to CNF, so there will be total two null production that we have removed.
Yeah,
Am I
correct.
right?
Yeah, these two.
Okay.
Were you able to understand the first one? You were saying you had a doubt a while back. So is D to epsilon clear? How is this happening?
Excuse me, ma'am.
Yes.
How AB will combine? It is yes into A, yes.
Yes.
So yes would come.
S should come. So so
Since it's
here,
not epsilon, so yes, consider.
okay.
The epsilon for B.
So epsilon is there
D
for
for
D.
the
So here in the production rule, just let me make the notations clear. So S is the start symbol, and we have D. D is here, right? So D is a non-terminal or a variable. And other than that, we have A and B, which are terminals. Yeah, which are terminals. And okay, C is also there. So A, B, and C, and epsilon is a null symbol.
Epsilon also terminal.
Yeah.
Ah.
Okay. So, so I think as we complete the solution, I think your doubt will also be clear. So let's just take it one by one. At the end, I'll again ask if you still have the doubt. Okay?
I say
Yeah.
the non-terminal, there are four non-terminals. One way.
Four non-terminals, like the solution you're saying?
Yes, yes, yes. ASB is one non-terminal. C is one non-terminal, and DC is one non-terminal.
No, so non-terminals would be only these. Only if you consider. So this is. So let's take this. So we back to the original problem, right? Over here, only D is the non-terminal. So S is also non-terminal. It's a start symbol. Hmm.
Compare A to B. ASB.
So
So yes is also a non-terminal.
so ASB. So this is itself a rule. So here A and B are the terminals. S is the start symbol, which is also non-terminal. Yes, but you cannot. So the the entire ASB is a combination of terminals and non-terminals. So that is why this is a context-free grammar. So in Chomsky normal form, we know that what is the criteria? A non-terminal could be expanded either as a single, so there should be a single terminal on this side, or there should be exactly two non-terminals, right? So we see a discrepancy over here. So that is why we need to modify the production rules in such a way so that we get the Chomsky normal form.
Okay.
Okay.
And when you say S leads to A, S, B,
Hmm.
uh, this A and B is considered as terminals, is it?
Yes, yes. So they are not variables.
Yeah.
We cannot further expand A and B into anything else.
Okay, is it is notation like lowercase is we mentioned in our terms?
Yes, we usually mention terminals in lowercase. So these would be the leaf nodes. We had.
Terminals.
Hmm. So in
Whichever in uppercase has to be considered as one of the non-terminal and divided.
yeah, so over here, so in this example which Sir had shown, right? So all the words in the lexicon, if you remember, were the terminals, right?
Yeah.
So similarly, A and B are like that. So they come at the, so they appear at the last step of derivation. You cannot further derive anything from a terminal. So they're like a terminal node. Okay. So are all the doubts clear? Okay. So we were here. We completed till 2 part A. Let's take 2 part B. So now we are handling the next null production, which is S to epsilon. So we see again over here, again on the right hand side over here, we have A S B. So if we replace S with an epsilon, we remain what we get is only A and B. So now this remains as it is. Now when I take this, what do I have? I first again write the thing that was originally there, which is S to ASB or D. And now I additionally add AB. How did I get AB again? I just placed epsilon over here and that gave me AB. So that is what I wrote here. And over here there's no more, so this has already been handled. So here there's no more epsilon s present. So this is the final production rule that I get after removing null production. Now I need to remove the unit productions. So in order to remove the unit productions, I need to. So what are unit productions? Unit productions are rule of the form A to B, where both A and B are non-terminals. So we need to first see what are the. So this is the latest production rule. So let's see what are the unit productions that are present here. So one is this one, S dash to S. Okay. Another one is this one, S to D, and here there's nothing. Okay. So these are the two unit productions that I have. So first let's handle this one, S to D. So in order to handle S to D, I see that what does D derive? D derives DC to C. So it's simply wherever, so here S to D was present, right? So instead of D, I simply write DC to C. So only change that has happened from here to here is you see that S is here, same, A is B is also same, AB is also here, just in place of D, I write DC and C. So this, by doing this, I handle the first unit production. Second one is this, S dash to S. And we know that S derives this. This is the current derivation for S. So I simply write S dash derives to be the same thing that S was deriving, and then the rest of the things are as it is. So right now we have handled three things. One was the point where start appeared on the right side of the production rule. We have removed the null productions. We have removed the unit productions, and now finally we have this. So there are two more steps that are remaining. So now we need to see, so on the right hand side of the production rules, where both terminal and non-terminal are appearing. So that is not allowed in Chomsky normal form. So what do? We add production rules such as capital A to small a, capital B to small b, and capital C to small c. That on the left hand side we have non-terminals, capital A, capital B, and capital C, and they're correspondingly deriving small a, small b, and small c. Okay. And now we simply replace them. So what do we have right now? So in place wherever the terminals were there, we simply replace by the corresponding non-terminals. So we have S dash now deriving capital A, SB, AB, DC, and C, and similarly for the other cases. Now once I'm done with this, only last step that was remaining is I have to see which are the cases where there are more than two non-terminals on the right hand side. So one is over here, we see S dash to A is B. So here three non-terminals. That is not allowed. We can have exactly two non-terminals. Again, over here. So these are the two cases that I need to handle. So how do I handle it? I add one more non-terminal, which is E, which would be deriving SV. And once I have this, I simply, wherever SV was there, I replace that with an E. And so finally, uh, this is the grammar rules that are obtained in Chomsky normal form. This is abiding by all the rules of Chomsky normal form. So the question was, how many non-terminals did I have to add? So one is S dash, another one is E, and A, B, C. So total 5. So is this
This
clear?
case also has to be considered again.
Yes, 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 yes.
And this process for deriving the solution we have another recorded in the sessions. The steps to be followed or to personalize and replace. There should not be more than two non-terminals in a single word.
So
Rules or anything different for this?
So rules for the Chomsky normal form are given in the slide. So these two rules that you see, exactly two non-terminals should be there on the right hand side and one termination symbol should be on the right hand side. This itself I've taken from the lecture slides itself. So this is mentioned.
Ma'am,
Yes.
what if the start symbol is derived directly as silent and there is no derivation of x? So if there is right hand side as itself, then we add new state as that, right?
Yes.
So if there is no as in the right hand side with the start state and it derives itself as silent, so what in this case? What happens?
S derives epsilon.
Yes, ma'am.
So I'll take up your question one by one. One thing that you said was S is not there on the right hand side. So simply an example would be S is deriving A, B or D. In such a case, if that happens, you don't have to follow the first step. You directly start from the second step. Second thing that you said was S is deriving epsilon. So if S is deriving epsilon, then so it's like an empty grammar. So S deriving epsilon means, so it's a starch symbol. It is not deriving anything if that is there. If S is deriving epsilon in that case, if that is there as a rule, okay. So yeah,
So it will not be in CNF, means it will not be derivable.
uh, yeah, probably. I think if I mean I do not have an exact example. If so, I think no, I don't think that would be the case. If S is deriving epsilon, then there's no point in like forming a grammar or creating a language because S itself is giving epsilon, right? That is the hmm.
Actually, ma'am, I have read somewhere,
Hmm.
apart from these two cases,
Yes.
there is also if start symbol derived, I mean implied as silent, then it it will be also in CNF. I think read somewhere whenever I see the lecture, whenever I try to solve the question.
Okay. Then maybe that's a special case. To be honest, I'm not aware of the thing that you're saying. Maybe that is correct. Maybe other people in the chat can confirm.
Okay, ma'am. And one more thing, ma'am.
Yes.
So how many total number of production rules? Production rules and steps are the same thing in this question.
So production rules would be these that I've obtained at the. I hope you can see my cursor. So total 1, 2, 3, 4, 5, 6, 7. So total there are 7 production rules that I have.
Okay. So production rules that we have derived at the last of the solution.
Yes.
Okay. Thank you.
Yes.
I have in the two-way solution.
Yes.
B derives
Yes.
When B derives DC or C.
Hmm.
So if you are eliminating B derives epsilon,
Hmm.
it will be D derives DC or DC.
DC or so when we are uh, eliminating D to epsilon, so forget about this. So we only have D to DC. So in DC, I have to plug in the value of D deriving epsilon. So when I plug in epsilon, epsilon is nothing. So we only have C. That is what I'm adding alongside DC, which was originally present. Okay. Any other doubt?
Can you explain the unit production alone for us?
Yes. So what is a unit production? Unit production are production rules of the form A to B, where both A deriving B, where both A and B are non-terminals. So that is what a unit production. So whenever we are doing this, we see what was the latest production rules that we had derived. So these were the latest. So here we have to see what are the possible unit productions. First is this one, S dash to S. Another one is S to D, right? So both S and D are non-terminals, and here we have nothing. So these are the two unit productions that are present. So I need to remove them one by one. First, let's take this one, S deriving D. So what we do is we check where S is appearing on the, sorry, where D is appearing. So in here D is not appearing, sorry, here D is not appearing. Here we see that here D is appearing. So how do I eliminate D from over here? We see what is D deriving. D is deriving DC and C. So we simply plug it over here. So that is what I have done.
How many our grammar it is deriving, everything we have to substitute.
Correct, correct. And so this is what you get. And similarly for the second one, you simply here what we do is simply take S and plug it over here. And that gives us the final one. Yes. Any other doubt?
No, ma'am.
Okay. Okay, let's go over to the next problem. So here we have to solve using the CKY algorithm. We have been given the sentence, children play cricket with friends, and we have to find the probability score for the most probable tree for the sentence. So please try solving this question. We'll wait for a couple of minutes and then we'll take up the solution.
we have probability scores given within the work.
Yes. So this is these are the rules that are given. I think so. So we'll be discussing two CKY problems today. So this is the first one. Maybe for this we can directly jump on to the solution and we can discuss. For the next one, we'll maybe take a little bit more time. Okay. So here, how do we solve this? So this is a sentence that is given to us. First, just briefly let us discuss what are the steps that are there in the CKY algorithm. So first we are given this sentence. So children play cricket with friends. So there are 5 words and we have to we need to, for each of the words, we need to form a table and then we need to solve the table bottom up. So let's try this. So um, yeah, I'm sharing an Excel sheet. I hope it's visible. So we'll solve it over here. Yes, okay. So these are the rules that are given to us. This is the sentence that is given to us. What was the first thing that was mentioned? So let n be the number of words in the input. Think of n plus 1 lines separating them, number 0 to n. So that is what we have done over here. So we have drawn lines. So 0, 1, 2, 3, 4, 5. This is for the sake of the simplicity of solving the problem in an algorithmic way. And now in the table, what we do is we number each of the each of the cells. So what is this? This is 0, 1. What does 0, 1 means? What are the words appearing in the span 0 to 1? Similarly, 0, 2, 0, 3. So similarly, I've filled all the cells. So let's take 2 to 4. What's this? What does 2, 4 means? 2, 4 means what are the words appearing in the cell from 2 to 4? That would be cricket with. Okay. Now let's try filling the cells according to the CKY algorithm. First, we start with the diagonal values. So over here, if I take this one, that is x01. So what is it? It is children. I have to see what are the production rules that is deriving children. So that is NN. So I can simply write NN over here, right? So NN is deriving children. Okay. So that gives me this. Again, now if I go over here, that is 1, 2, that is play. So one thing that to notice along the diagonals, I only have individual words. So those, so over here, we have to see what are the corresponding pre-terminals that are deriving these terminal words. So what is there for play? We have for play, we have VB. For cricket, we have NN. For width, I have PP. And for friends, what do I have? I have NN again. So now I've, yes, so I filled this row, this diagonal. Now I move one step up. So we are doing bottom up. So next is this one. So this and this. So these are what would be filling. So what is this? This is 0, 2. What does 0, 2 mean? So 0, 2 would be accounted as, so how do I split it as? 0, 2 would be split as 0, 1 and 1, 2. Okay. So what is 0, 1 and 1, 2? So these two would give me an idea what this would be. So I have to find what is the non-terminal that is deriving NN and VB on the right hand side. Can we find anything? NN and VB here. Here we find VP is deriving NN and VB. So this would be VP. Okay. Next is this one. So this is 1, 3. So 1, 3 it will be 1, 2 and 2, 3, right? So it will be 1, 2 and 2, 3. This and this. So is there anything that has, is there any rule which has VBNN on the right hand side? This one again VB, correct? Next we go to this one. For this, so it is 2, 4. For 2, 4 I have to take these two, NN and PP. Is there anything with NN and PP?
Maybe.
No, it is PPNN. So I need NNPP. Is NNPP there? No, right? So this would be nothing. So this would be null. Again, it's PPNN. So PPNN is here. That would give me PV over here. Yeah, correct. So now I again move one step up the diagonal. Now I have this one, which is 0, 3. So how can I get 0, 3? 0, 3 can be obtained as 0, 1, 1, 3, 0, 2, 2, 3. So let's see. 0, 1 and 1, 3. So that is NN and VB, NN and VP. Is there any rule with NN and VP? Here. Here we have S. S is giving NN and VP. So here we can write S. Okay. Another one. Yes. Which one? This one. Okay. Yes. Just a second. Yes. So here what we are doing is we are at the 0, 3. So this is x03. So in order to find what is x03, we need to check. So we are going in a bottom-up fashion, right? So from the already computed values, we need to see which are the most relevant ones. For x03, x03 is children play cricket. So how can I break these? How can I break children 3 cricket? One way I can break it as 0, 1 to 1, 3. What is 0, 1? 0, 1 is children and 1, 3 is play cricket. So that could be one breakup. Another one could be 0, 2 to 2, 3. What is 0, 2? 0, 2 is children play and cricket. So these are the two possible ways I'm breaking up these sequence of 3 words. And then see, so for now for each of the decomposed parts, so x01, x13, all these I've already pre-computed. Now I have to see that are those, if I combine those pre-computed non-terminals, if I'm getting some other non-terminal. So let's see. For x03, what I have to check? I have to check 0, 1 and 1, 3. So that is this and this. So is NN and VP giving anything? So I have to check, is there any production rule where NN and VP occur on the right hand side? So I have this one, right? So that would give me an S. So here, what does this mean that I'm getting an S? It means that here children is, so children was derived from NN, and here I took this one, VP. So play cricket was a verb phrase, and which was further derived from VB and NN, where play was derived from VB and cricket was derived from NN. So that is how all these things are falling into place. Okay. So I only computed 0, 1.
One small addition here. I understand that this model, like you just take the adjacent diagonally elements alone, right? Because it is contiguous. Why do you start from 0, 1 to
0, 1, 2. Okay.
the current one, whatever you're deriving 0,
This
2?
one. Mm-hmm.
So why starting with 0, 1 actually? You can just consider 0, 2 and
0, 2 and 2, 3.
1.
0, 0, 2 and 1, 3. So what does 0, 2 mean? 0, 2 means what are the words between 0
Play.
and 2? So children play. And 1, 3 means what are the words between 1 and 3? Play cricket. So there's an overlap of the word play, right? Hmm? So 0, 3 simply means all the words that are present between 0 and 3. So that is children play cricket. And when I'm doing in Chomsky normal form, I know that on the right hand side there could be uh, exactly two non-terminals or a terminal. So terminals I could only obtain from the first diagonal that we evaluated. After that, all we are dealing with is non-terminals. So at a time, I can only deal with two non-terminals. So that is why I'm breaking 0, 3 into two parts, two segments. 0, 3 can be divided into 0, 1 and 1, 3. Another one to 0, 2 and 2, 3. So I have two segments. Each of the segments would give me a non-terminal which I can combine to another non-terminal because my grammar is in Chomsky normal form. So here we have children play cricket in 0, 3. One way we divided was 0, 1, so children, and then again from 1 to 3, which is play cricket. So that was one. So here that gave us an S. Now another way we could formulate this was 0, 2, which was children play, and another segment would be cricket. That is 2, 3. So that was 0, 2 and 2, 3. That is VP and NN. So is there anything with VP and N? So that
Yes, sir.
so that would be S again. Okay.
Can we take 1, 2 and 2, 3? After 0, 1 and 1, 2. Can we take 1, 2 and
1, 2 and 2, 3.
3?
1,
After
2 and
from
2,
the back
3.
to the front.
So 1, 2 and 2, 3 would give me 1, 3, right? So 1, 3 we used 1, 2 and 2, 3. We obtained 1, 3 based on that only. Is that your question? Hmm. So here we got an S. Okay. So let's move ahead. So here we got an S, right? Next was next we go for this one. So it is it is 1, 4. So how do we get 1, 4? We get 1, 4 from 1, 2, 2, 4 and 1, 3, 3, 4. So what is 1, 2, 2, 4? 1, 2, 2, 4 is this 1, 2, 2, 4. So that gives us nothing. Another one is 2, 3 and 3, 4. NNPP, is there anything with NNPP? No, right? So there's nothing with NNPP. So this would be nothing. Finally, we have 1, 5. Sorry, 2, 5. We have 2, 5. For 2, 5, we take 2, 3, 3, 5, 2, 4, 4, 5. So what is 2, 3, 3, 5? NN and PB. NN PB is here. That gives me a verb phrase. And anything else? 3, 4, and 4, 5. Does PPNN give me anything? PPNN gives me a PB. Okay. So now we have this. So I hope what I did was correct, right? 2, 3, 3, 5. NN PB. Yes. Oh, sorry. NN PB is. Pardon? NP. This would be NP, right? NP. Yeah. Yeah, okay. Now let's go over here. So we have 0, 4. So 0, 4 I can obtain in 0 to 1, 1 to 4, 0 to 2, 2 to 4, 0 to 3, and 3 to 4. So there are multiple ways. So one would be this one, this and this. So let's take that. So this and this gives me nothing. Next would be VP and this. This also gives me nothing. Then S and PP, that gives me nothing. So here I have a null. Next we take up this one, which is 1, 5. Yeah. So for 1, 5, what do we have? 1, 5, we have 1, 2, 2, 5, 1, 3, 3, 5, and 1, 4, 4, 5. So we start with this and this. So what does VB and NN, this does give me anything? VB and NN. So that gives me a verb, VB and NP. PB and NP, it gives me a verb phrase, right? Yeah. And do I have anything else? And VB and PB, does VB and PB give me anything? No. So I only have VP over here. And another way was, so I tried with this one, 1, 2, and 2, 5. What is 1, 3, and 3, 5? Does VP and PB give me anything? No, gives nothing. Then this is null already. So this with this would again give nothing. So I have VP over here. Finally, we go to the last cell, which is 0, 5. So 0, 5, I have to check 0, 1, 1, 5, 0, 2, 2, 5, 0, 3, 3, 5, and 0, 4, 4, 5. Okay. So this and this. Does NN and VP give me anything? Yes. S. So I got an S over here. Does VP and VP give me anything? No. Does S and NP or PB give me anything? No. And after that, it's just null, right? So anyways, we had got an S, but I still checked the other options. So since we have got an S over here, it means that the sentence is grammatical, and we were able to derive the sentence from using the grammatical rules. So this was the CKY algorithm, how we proceed with it. Now the thing that was asked is to find the probability score. So for probability score, one thing is, I think what was done in the video lectures was, as we are computing the CKY algorithm, we can keep on computing the probability score. So that also you can do. I tried a slightly different thing over here, which is like, now we have the CKY algorithm. So this was the result. From there, we can construct the parse tree. So if we draw the parse tree, and now we know what are the probability corresponding to each production rule. So if we simply multiply all these values, right? If we simply multiply the values, we'll get this to be the answer, 1.62 into 10 to the power minus 6. So that would be our answer. So any doubt in this question?
Ma'am, multiply with all values of
All the values,
what values?
all.
All the values like children, NN, play, BP, these all are the values.
So these are the numerical values that you can see. So I'll explain. See over here we have S to N and VP. That production rule has a probability of 0.50. I'll show you over here. See this one, right? So that
So
is
we will take the last column to
hmm.
calculate the probability.
Yeah, so only for the production rules that have been used in this particular pass tree. So so if you can see these numerical values that I've written corresponding to each of the nodes. So these are the values that you need to multiply because these were the production rules that we utilized for this sentence. So you have to multiply 0.50 into 0.15 into 0.20 into 0.30 into 0.40 and likewise the remaining.
In this column, we fill the values in diagonal way. So make the combination on the basis of diagonal pair. Just like you have filled here on the place of 3 cricket, 0, 3, and 3 cricket, where you have written the S. So you have not taken the BP because BP are the same. This is true or something else. Actually, I didn't understand and I got confused during this.
No problem. No problem. So you're saying computing this last cell you're saying?
No, ma'am, in the starting third cricket for the cricket.
Acha, here. So here is like we are in the middle of the sentence. The sentence that is given to us is children play cricket with friends. So if we instead of taking it's if we remove with friends, children play cricket is still a valid sentence, right? And that can be obtained using the grammar rules. That is what this S implies. But we can't stop there because for us the sentence that is given is children play cricket with friends.
But the value will be there pointer here.
Here,
Whether we consider NMVP or the other ways is VP value pointer.
yeah. So the first two production rules on basis of that you're saying, yeah, yeah. So one thing that I did a mistake was I was explaining the slide, but I did not share it. So this is the final pass tree that we obtained on basis of the CKY algorithm. Okay, so we simply draw the pass tree and plug in the probability values corresponding to each of the production rules. Then now all we need to do is simply multiply these values. These are the probability values. We simply multiply them, and that would give us the probability of the sentence. That would be the answer in this case, 1.62 into 10 to the power minus 6.
To fill the values of the current cell, you didn't take the immediate diagonal value.
We took that also. So maybe we can go over one more step once. So let's take this one. Can you see my cursor? So let's take 1, 3. Okay. So I need to calculate the value of 1, 3. So would you like to try once? How should I go about if I have to do 1, 3? So what does 1, 3 mean? 1, 3 means play cricket. For play cricket, I'm computing how could it had been derived. Okay. So 1, 3 could be decomposed into two segments. One is 1, 2 and 2, 3. Right. So that is this one and this one, right? So VB and NN. So that is why I checked. So now we are checking the corresponding diagonals that are there like about this cell. So VB and NN. So VB and NN can be derived from VP. So that is why I write VP over here. Is it clear? Should we take another one?
Ma'am, the blank empty you can take like this.
This one. Okay. So this is 1, 4, right? This one. So 1, 4, we are checking what are the different ways it could have been derived. So for 1, 4, we need to further decompose it. So how do I get 1, 4? 1, 4 can be 1, 2, 2, 4 and 1, 3, 3, 4. These are the two ways, right? So 1, 2 is this one, VB. And here in 2, 4, there was already a blank. So there was no way in 2, 4 could be derived. So we further try to combine these two, there is no way. Okay, so that is why I get a dash. Again, further one thing was 1, 3 and 3, 4. VP and PP. So can I combine VP? So these are two non-terminals, right? So is there another non-terminal which is expanding into VP and PP? So I have to check if VP and PP are there on the right hand side of any production rule. Can you find any production rule?
No, ma'am.
No, right? So that is why it is a blank. If there was, say, maybe X was deriving VP and PP, we would have written X over here. We are
Okay,
just
ma'am.
combining pairs of terminals at each step and finally reaching to the S over here. So at each step we are combining two non-terminals. Right? That is what we are doing.
And ma'am, one question is this.
Hmm.
Here the sequences matter. Like here is given BP tends to BBNN and BP tends to NNBV. Somewhere they given the value for the NNBV, so we have filled the BP, but we have not taken the upper value. Like here are the same BP, so
So it
message
has to be
confused. But
completely determined by, so you have to blindly follow what are the production rules given to you. If that is allowed, so say here it is given NP is NNPB, you have to follow first NN has to come and then PP. If it is PBNN, then PBNN should be the order. Is determined
oh,
by how the non-terminals are appearing in the production.
okay, ma'am. Thank you.
Okay. Any other doubt? Um, okay. So what I said. Correct. What Suvarna has written is correct. Hmm. Yes. Next, let's go on to the next problem then. It is a similar problem, but it's a shorter problem. So this time I have a shorter sentence. Children enjoy music. So for this, again, I have to do the CKY algorithm and find what are the number of past trees and the probability score of the most probable tree. So you can note down the sentence, which is children enjoy music. I'll skip the slides to over here. So you see the rules from here. And the sentence was children enjoy music. So try solving the problem. We'll wait for 1 minute and then we'll discuss. We are solving this problem right now. Children enjoy music. This one. Question number 4, we're currently solving.
Grammar also share the same language.
Same grammar.
Ma'am,
Yes.
like here, Anand implies cricket. So in the case, cricket slash football. That means Anand implies cricket and followed by football. Is it?
And so if rule is given, NN derives cricket slash or the vertical bar, it means NN can derive both.
Yes.
It could derive cricket also, it could derive football also.
Means either or. We
Yeah,
can
either
take
or.
the cricket. Okay. But man, one doubt also, like there are two, just given in this example, Anand implies cricket and Anand implies football.
Hmm.
Okay. So in both cases, it's cricket slash football, and in the
So
bottom case, football slash cricket.
hmm.
So does it mean the same?
Yeah, so it means the same. So what you are saying, that is in the case of normal context free grammar. This is probabilistic context free grammar. Okay, so in normal context free grammar, you can write NN deriving, it could derive any of the words. NN could derive cricket or football or baseball. So all these three in any order could be written separated by a vertical bar. It means that NN could derive any of those words. But here you can see that so NN, so in probabilistic context free grammar, so NN deriving cricket, NN deriving football, and NN can derive all these things as well, right? So all these probabilities should add up to 1. Wherever the left hand side is the same, so NN deriving something. It could be children, it could be friends, music, cricket, football. I hope I'm not missing on anything. So all these probabilities should add up to 1.
So ma'am, in the calculation, it can be problematic now. Like if you have taken an implied cricket in place of football, so the value will be 0.15. But if you take the last one, bottom one, then the value will be 0.10.
So you have to take,
So,
so depending on what is the sentence that is given to you. For example, here the sentence was children play cricket. So here you have to take n into cricket, which has a probability of 0.15. If the sentence was children play football, you'll have to take this one. So depending on what is the sentence that is given to you,
no, ma'am, I'm saying in the case if both are given in the class,
then it
in the
won't be
parallel,
probabilistic.
individually.
Then I don't think there would be a probability value mentioned beside it. So it would be simply n. So it would be like this, right? This is the slash you're mentioning.
Mm.
So here it would be like, so here it would be NN deriving cricket, football. So it could derive this or this.
Okay. Just if in the sentence we have given cricket here, so we have taken the cricket.
Hmm.
If we have given the cricket plus football, right? Suppose if we have given the football,
Hmm.
then we can consider the last one firstly. Wherever we have to given the football plus cricket, is it? We can do it as or we can do cricket plus football. And then we can go with which one?
So so it would be like it would be so it could be either one of the words. Either one of the words would be here. It couldn't be like at one position. It could be either cricket or football, whichever it is. That would be derived from an NN, from a noun. So slash means that. Slash means that itself. Maybe I'll just check in the slides if there's any other example. I'll discuss that to clear your doubt. Just a second. So I hope you can see the slides over here, right?
Yes,
So here you see that, for example, here the word read was there, right? So that is why. So here if you see, there would be a rule where verb is deriving read. So that is why we go that okay, how is read derived? Read was derived from a verb. So instead of read, it could be write also, or wrote also. The man wrote this book. So if wrote was there, again wrote would be a verb. So that is what it means. Does it make sense? So here you see, this is what you're saying. So verb can be book or include or read. Noun could be book or flight or meal or man. Noun can take either of the values.
Yes.
Okay. Um, okay, let's discuss question number 4. So here, if you do the CKY parsing, so here we'll see that we kind of, so at the last cell when we are doing, we'll observe there's an S, two S's are coming. So that means that there are two possible parcels for this sentence. So one is this one, where from S, we're first going to NNVP. NN is deriving the children. And I have another separate verb phrase, which is enjoy music, where enjoy is VB and music is NN. Another way is that children enjoys the verb phrase and music is the noun phrase. So these are the two possible past trees. Now what do I need to do? I need to compute the probability of each of the past trees. So how do I do that? I simply multiply these values. So this is for the first one, NN and VP1. So I have 0.5 into 0.15, 0.3, 0.2, 0.12. That gives me this value. So 0.54 into 10 to the power minus 3 is the value for is the probability for this particular pass tree, whereas for this particular pass tree, it is 0.45 into 10 to the power minus 2. So this one where S is being decomposed into NN and VP. So this is the more probable pass tree, and so this would be the answer. Okay.
And you're summing up both, is it? Or only one?
So the question is the probability score for the most probable tree. So if it was asked probability score for the entire sentence, then we had to sum it up.
How did you choose which trees more always?
So just based on the probability values. So for each of the pass trees that I obtain, so this is pass tree 1 and this is pass tree 2. For pass tree 1, I multiply all these probability scores. Okay. And that gives me 0.54 into 10 to the power minus 3. Whereas for the second pass tree, if I multiply all the values, I would get this one. 0.45 into 10 to the power minus 3, which is a lower probability score compared. So based on that, we decide. Any other doubts? Uh, yeah.
Why this actually we can the first one is the matches, right? There's B1, NM and BP, SBB and NM.
Hmm.
Why do we come up with the alternate for that BP and NM?
So if we do the CKY algorithm, right, we will come up with, so in the last cell, we'll see that we are getting S comma S. So whenever we are getting this, it means that this tree could be derived in two possible ways. So we can quickly try solving maybe. Um, okay. So this would be the CKY algorithm. So let's be a little bit quick this time. So for,
Nothing shared.
oh, it's not shared. Oh, sorry about that. Yes, hope it's shared now. Right. So, so what we have, so for children, how do we derive children? From NN, right? How do we derive enjoy? We derive it from VB. How do we derive music? For music, I have NN, right? Now when I'm at enjoy, I can derive it from NN and VB, right? What does NN and VB give me? VP,
Yes.
right? And what does VB and NN? So now I'm at this cell. What does VB and NN give me? Where's VB and NN? VP. Okay. Yeah. So now when I'm over here, what do? I have, so what is this? This is 0, 3. So 0, 3 can be broken down into 0, 1, 1, 3, 0, 2, 2, 3. What is 0, 1, 1, 3? This and this. So NN and VP, does NN and VP give me anything? That gives me a sentence, right? And again, if I take 0, 2 and this, what is VBNN? That is also a sentence, right? VBNN. So I get two possible ways of forming the parse tree.
So basically, it's found in the grammar only we consider, right?
Correct, correct. Yeah, yeah. If this rule was not there, S2 VP, VPNN, then there would be only one valid one, which was the first parse tree.
You can just share that Excel with me.
Okay. So any doubt over here?
No, I think that's
Okay. Does anybody else have any other doubt?
No, ma'am.
Okay. So let's go on to the next problem. So this is a problem based on the inside outside probability. So this is directly from the slide. So let's be a little bit quick with this. So we are given this statement. We need to say what does the LHS interpret.
again share as to that.
Okay, sorry about that. So yeah, so we are doing question 5 right now. So here we need to do the inside. This is a problem based on the inside outside probability. So we are given this statement. Okay. So what is the left hand side? Which is probability of children watch football, enjoy music, given the N3, 4 and G. What does this mean? What does this represent? So that is what we have to say. So this is a question directly from the lectures and the slides. So let's just wait 1 minute, then we'll directly jump to the solution. People, like if anybody knows the answer, please post your like answer in the chat. Okay, let's discuss this. This is a like a theoretical problem. So in this case, the answer would be Z. So what does this mean? So this means this is the probability of the sentence. Children watch football, enjoy music. Given the grammar G, and so what does this N34 means? There's a consistent spanning of the segment. Football, enjoy. This one. What does a consistent spanning mean? So there is any possible non-terminal which is deriving this span, football enjoy. That is from words 3 and 4. That is what this means. Okay. Is it okay? I think this is like if you go to the slides, this would be clear. Let's go on to the next one. So this one is based on top down and bottom up cursor. So again we have been given four statements. We have to say which of these are true. This you all can quickly try once and try posting your answer in the chat. Okay, quite a few of you have tried this problem. Mm, so let's hear from some of you. So Suvarna thinks it's C. So would you like to share your thoughts?
Man, actually, top-down parsing starts from the first non-terminal in the given grammar. So whatever valid options are there to explore that non-terminal, they are only explored, and not all the options which can connect to the actual sentence will be explored in that case. That's why I thought C is the correct.
Okay, okay. Mm, so Lokesh thinks it's A and D. So how about Lokesh? So what do you think A and D are the possible answers?
We are not given the passing actually, but this uh, information I have, this is CMD because often we start with keywords tags and we end up passing to the sentence given sentence. Whereas from bottom up to we start with the sentence and we end up with the tags.
Okay, I think it's
So
actually
not
the
like that.
opposite. And oh, it's okay, it's fine. Um, it's okay. Well, thank you for trying. Okay. Um, let's hear. Sorry, maybe I'm pronouncing it wrong. So just Lalitham Bigai Lalita. Okay, she left the meeting. Okay. How about Chandrakala? You have said it's A.
Yes, ma'am.
Yes.
Um, the top is never explore options that will not lead to full path, but it can explore many options that never connect to the actual sentence. So I choose option C.
Okay. 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 Fine. Let's discuss the solution now. Would anybody else like to add anything before we discuss the official solution? Okay, all right. Let's discuss. So the answers are A and D. So what happens in top-down approaches? We start from the S symbol, then we enumerate all possible ways we could expand that, and as a result of that, we explore a lot of options that will never lead to a full pass, but can explore options that never connect to the actual sentence. So, for example, let's go on to the slides for a second. Just a second. Um, yeah, okay. So let's see one example of top-down parsing. So here, Sir had discussed this sentence, right? Book the flight. So what do we do in top-down parsing? We start with S, then we expand it. We keep on expanding it and we see that, okay, here we see, okay, so the POS tags are not matching. So pronoun could never give a book. So we remove this. So like that, we start from the top and we enumerate all possible cases and we finally see is there a possible case that could derive the sentence that I'm looking for, which is this one, book the flight. But in attempt of doing this, we tried many other sentences as well, right? Whereas what do we do in bottom up? We start from the words, book the flight, and then we go one step at a time. We first see what are the POS tags that could have derived this, and then we try combining them, right? So this way, so we proceed in from the bottom to the up. So as a result of this, what could happen? You see, so finally, this is what we get, correct? So now let's go on to the slides again. Yeah. So what does bottom up? So bottom up never explores options that do not connect to the actual sentence because we're starting from the actual sentence, right? We always explore options which connect to the actual sentence, but it can explore options that can never lead to a full pass. So there were many, so we saw in the slides, right? um, see in these cases. So in these cases, we see so this is a separate segment and this is a separate segment. It's not leading to a full pass, right? So these are instances where it is like so it is connected to the sentence, but it's not giving a full pass. Whereas in case of top-down parsing, it's the opposite. Any doubt? Any doubt in this question? Okay, I hope it is clear. Let's try this question. There is another CFG question. So again, we have to find the number of how many non-terminals needed to be added to convert the grammar to CNF. We have to follow the exact same steps that we discussed in a few problems before. So just try this. Try this for a couple of minutes. We'll discuss this. Okay, I think we can discuss this problem. So we follow the same steps. So it would be a bit of a repetition, but still it's a different problem. So let's go through it. So here again, so this is the production rule that is given to us. Again, we see that since this start symbol S occurs on the right hand side, here as well as here, production rule, what we do is we create a new start symbol S dash and we add a new production rule S dash to S. So we created this new symbol S dash and we added this production rule. The rest is as it was in the original problem. Next step is removing the null productions. What are the null productions over here? This one, B to epsilon, B to epsilon, this one. Again, we see here we have A to B and B again goes to epsilon. So A to epsilon is also another null production. Let's remove them one by one. First, we remove B to epsilon. So for that, what do? We see there is B occurring on the right hand side. Here there is no B. Here there is a B. There is a B in AB. So we replace B capital B by epsilon. So that would give us only A. So that is what we have added. So S goes to what was originally there, ASA and AB, and alongside that we have added the small a. Okay, that was a result of replacing capital B by epsilon. Next is we have this one. Here again B is on the right hand side. So if we replace B by epsilon, what do we have? We have an epsilon. That is what we have added here. And finally this one. So B to epsilon we already handled. What remains is capital B to small b. Okay, so this is the production rule that I get after handling this null production. Next one is A to epsilon. First one remains as it is. The second one, here we have S to ASA. So there are two A's. So one thing that we can do is we can replace the last A by an epsilon. That would give me AS. Another one is we could replace the first A by an epsilon. That would give me SA. Or I can replace both the first and the last A's by an epsilon. So that would give me simply S. So that is what I have over here, right? So here the first part is as it was. Rest is what I get after handling the A to epsilon part. So these are the ones that I've added over here. These three: AS, SA, and capital S. These three. Next, I had this one. Here, there's no A on the right hand side, no A on the right hand side. So these are the rules that I obtained now. Finally, next what I do, next I have to remove the unit productions. So there are four such unit productions over here. So S to S, S dash to S, A to B, and A to S. So if I remove them one by one, finally I would obtain this. So that is not there in the slides. So as we discussed it previously, so this is not elaborated over here. But once you're done with it, you can check that this is what you would get finally. Okay, very similar to what we had done previously. So now that we have this, what is my next thing? Next, I have to handle production rules which have more than two non-terminals on the right hand side. So that is this one. ASA is over here, AS is again over here and here. So what do? I simply add this production rule X to SA. Okay, and wherever SA was there, I put an X. So here I have AX, here also I have AX. Like that I replace. Finally, what I have to do is there are production rules which contain both terminal and non-terminal. So, and the only non-terminal that I see over here is this small a. So I need to account for that. So I add one more rule where a non-terminal y is deriving small a. Then I simply replace that. So wherever wherever simply a was appearing a single terminal, that is abiding by the CKY rule. But wherever there was a combination of a terminal and a non-terminal, whereas here you have AB, here also have AB, here you have to replace small a with a capital Y. Okay, and finally this is the answer that we get. And here we had to add three symbols, S dash, X and Y. So that is why the answer is 3.
Why not terminal B? Okay, that has a non-terminal capital B.
Yes, yes.
So we have to give a count what are new non-terminal B.
Correct. So what are those? Those would be S dash, X and Y.
Ma'am,
Yes, sir. One by one, go ahead.
ma'am, if there is rule like A tends to small a, I mean non-terminal implies two terminals. So we can remove this rule in the PNF form.
So you're saying of the form AB like that. Hmm. Sorry, I did not understand your questions. I'm asking.
Ma'am, if non-terminal implies
Mm-hmm.
two terminals in the PNF form, or we have
Okay.
the right from
Huh.
the CFD. So what will be the case?
So that was
What
here,
will be
right? In the first problem that we had tried, if you remember this one? The first CNF problem that we tried today, here there was the case, right? This S dash is deriving AB, right? So what we did was, in handling AB, I had to replace both small a. So to handle for small a, I had to include this capital A deriving small a, and to handle B, I had to include capital B deriving small b. So like that, ultimately S dash deriving AB would be replaced by S dash deriving capital A and capital B. So this would be again two non-terminals.
so this is because of this. I think so this comes by the if S implies to
So in
A capital S B.
so this is an example, as you said, no? Your example set was there's a non-terminal that is deriving two terminals, right? Which is S dash is a non-terminal over here. AB are two terminals over here. And
Yes,
and what is the rule that I have um, in this what I call in CNF? There only
PNF.
these two are allowed. Either there would be exactly two non-terminals or there would be one terminal symbol. Okay, so here what we had was two non-terminals, so that is not allowed. So I have to replace both by a terminal. So Small a would be capital A, small b would be capital B, where both now a and b are variables. They're no longer terminal symbols, they're non-terminal symbols, and exactly two non-terminal symbols, which is allowed according to CNF.
Okay, ma'am. Okay.
Hmm. What about AS? So I think you're asking, so Chandrakala had a question. What about AS you were asking? So here I have ASA. So you can either combine AS to be, so you can either say X is deriving AS. In that case, you can replace, so this would be XA, or you can combine SA also. So we had one, the first question was that, no, that where whether more than one CNFs are possible. So that would be another alternative solution, so where we would get a different CNF.
From in unit production,
Yeah.
no unit production, we have taken four things. S gives S, S dash gives S, A gives B, A gives S. So from the first grammar, we haven't taken S gives A. Is it not possible? This A is also a
So it has to be individual cases. So as you see, is there S to directly A anywhere? No.
not directly.
So it has to be direct. So it has to be of this form. That, for example, we see A to B, right? So A to B, like that. There should be a non-terminal deriving another non-terminal. Single,
Okay.
like that.
So if it is combining, we cannot take it.
No, right? No.
Yeah.
Ma'am, one more doubt.
Yes.
Like as start state implies on non-terminal, and this non-terminal is not in the grammar. I mean, given language. So what will be happening?
S is not in the grammar, you're saying, this one?
No, ma'am, no. Please, as is implied as or someone any non-terminal of the given grammar in the given language implies another non-terminal, single non-terminal,
Okay.
we can say, and this non-terminal is not giving any other. Means this the derived non-terminal is not given in the language anywhere. So what will be the case?
Then there's no way to handle it, I mean. So you're saying that here A is given B, but B is not deriving anything. You're saying, right?
Yes, ma'am.
So in that case, there's nothing. So in that case, we have to leave it as it is.
So it will be not in CNF.
It won't be, it would be. So we won't be able to substitute it. So see, so here we were able to, so A to B and B to small b was there, right? So here we replaced A with small b. So that substitution would not be possible. And whether it would be finally in the CNF format, that you have to see, like you have to consider all the rules, right? All these things you have to consider. Finally, if you see it's not going by the rules of CNF, then it won't be possible. You have to go through all the steps.
Okay, ma'am. Then that language what be ambiguous. Means not convertible in the CNF, right?
If finally you get that it is not following the rules, then it is, yeah, as you're saying.
Okay, ma'am.
Ma'am, I have a doubt from previous time.
Yes. This one?
Ma'am, yes, ma'am. In the second A step, that A implies B as and as ma'am. Can you please explain that?
This one? Where I'm hovering the mouse? This one?
Up.
B to epsilon?
Ma'am, A to B S epsilon. Y epsilon is there.
Okay. So here, what we are doing here, we are removing the this null production B to epsilon. Okay. So what do we see? We see where is B appearing on the right hand side. Okay. So here in this rule, A to B to S, here B was appearing on the right hand side, and if we replace B by an epsilon, we simply get an epsilon. So that is why epsilon is here. That is how we are handling for this case. So this was A deriving B or C was already there, and now to handle for this we have this epsilon.
Okay, ma'am.
Okay. Any other doubts? No? Okay. Uh, okay, all right. So then I hope if there are no more doubts, we can conclude the session for today. So thank you for joining the session. We'll conclude it. Thank you.